Hello, class. We are going to do section 5.2 now on the recorded lectures, continuing on probability. This section talks about what they call the addition rule, or what happens when you try to find the probability of an event occurring or another event occurring, and that's called the addition rule. So the first thing that we need to think about is these are called in the probability and math world compound events. And I think the best way to start is not to go to the slides, but let me just show you an example here on the whiteboard. And what we have here is the dice problem, where we have a single die. And as I put it here, we have 6 possibilities, numbers 1 through 6. So what would be the probability of rolling a 1 or a 2? Well, one way to think about this is what's the success? Well, success of that set would be either a 1 or a 2. So one way to think about that is that we put 6 on the bottom, and here's our success rate on the top. And when you do this, you're going to have to, if they enter it as a fraction, you're going to have to reduce it. Not on a quiz or exam, but you don't have to worry about that on when I give you a quiz or exam. You could just leave us 2/6 if you want. So the other way that we think about it, especially when these compound events get more complicated, is that we can think about this as an addition. So you can think about this as the probability of 1 plus the probability of rolling a 2. And so how does that work? That's 1 out of 6 plus 1 out of 6, and that equals 2 out of 6. So you can see that we get the exact same answer. So say like I asked the question, what's the probability of doing an even or an odd? And you're probably saying, that's kind of weird. That should be all of it, right? And that is true. Because if you look at the even, that would be 2, 4, and 6. And if you look at the odd, that would be 1, 3, and 5. So you put that together, that would be 6/6. Or if we use our new addition rule, probability of even plus the probability of odd, that would be 3/6 plus 3/6. And you could see that we get 6/6, which is a 1. But what happens if we do this? The probability of doing an even or the number 2. Well, if we take our way that we were doing that, right? And we just add up probabilities of success, right? That's 1, 2, 3, 4. So that would be 4 divided by 6. Or if we did probability of even plus probability of a 2, that would be 3/6 plus 1/6 again, and we'd get 4/6. Well, that is not the right answer. And the reason being is we have something here where in the 2 sets we have, you see the number 2 occurs in both of them. And you can't count a data item more than once when you do the probability. So what we want to do in this case is we have an equation that looks like this. The probability of even plus the probability of 2, and then you have to subtract what's common. And what we consider this is called an and function, even and 2, where they're common. And so when you do this calculation, this would be 3/6 plus 1/6. And where are they common? Well, we have one point that's common, right? So that would be minus 1/6. So we get 3/6. So with that example, I'm now going to show you some definitions and walk through a couple more calculations for you. So the first definition that we should talk about is this idea that we use is called mutually exclusive. And that's the idea that two events cannot occur at exactly the same time. Like when we went back to our dice problem, you can't get a 1 and a 2 at exactly the same time on a single roll, right? You can't get an even or an odd. So both of those are mutually exclusive. But you could see this one here, even or 2, is not mutually exclusive. So when we do these calculations, we have this formula here. And this is the role of addition, where you're looking for two events, the probability of them occurring. Well, again, you add the two individually, and then you subtract the overlap. So if the events are mutually exclusive, the definition of mutually exclusive is the probability of the two events occurring at the same time, which is an and, would be 0. And so you could see that when we do these calculations, they would cancel out. So say like we had so continuing, here's more of a statistical type of calculation given, say like we have, 1,000 adults that were asked this question, that you're likely to vote or not to vote, and do you favor or oppose a certain law that would support higher education? And you can see that we have a table that indicates that. And so what I'm going to do is walk through some of these calculations. And here would be the questions. But what I'd like to do is go to the whiteboard and show you how to walk through these more of a step-by-step. So what I did here is pause for the recording for a minute and very messily wrote the numbers up here. And you'll see that when you do probability calculations, especially in this table format like this, it's very useful to have the totals for the columns and the totals for the rows as well. Because you'll see that when we do this calculation, you will need those for the denominators for a lot of them. So the first question is, what is the probability that a randomly selected adult is likely to vote or favors the law? So the probability of V or the favor. So this is the addition rule, right? So that would be the probability of favor or voting, excuse me, plus the probability of the favor minus the probability of voting and that's the overlap favor. So you could see the probability of voting is adding this first row here, right? So this is the total. And the likely voters, right? And so that would be out of 1,000. So that would be 721 out of 1,000. So what is the probability of a voter being in favor of the law? Well, that's this column here, right? 523 divided by 1,000. And then the question is, where's the overlap? Well, the overlap is the being in favor and voting. So this number is the overlap. So that if you did that, you would subtract 372 over 1,000. And so you get out your calculator and you would end up with 872 over 1,000. And say like we did 3 decimal points, that would be 0.872. So continuing, let me show you one more calculation. This one I'm just going to do right on the PowerPoint here. And so this is the idea of calculating when there is no overlap. We did that on the dice with the 1 or 2. Let me show you what it looks like with data, more of a statistical way. So here it says in recent Olympics, 11,544 athletes participated. Of them, 554 represent United States, Canada, Mexico, etc. And so it says these events are mutually exclusive because you can't represent 2 countries, right? So here we have what's the probability that Olympic athlete chooses at random represents Canada or the United States. So the Canada is 314, which would be the second one here. And the US would be 544. Or 554, excuse me, which is the first one. You add those together, and then you divide by the total, which is 11,544, and you can see you get little, but over 7.5%, 0.075191. Again, be careful when you enter these in your ALEKS program. Make sure you see what they want you to round to. So the other section, or other topic in this section, excuse me, is this idea of complement. Sometimes it's called negation. And it's the idea of calculating the not function or the idea of something not happening. And one of the classic examples of this, again, is the calculation of the dice problem. And so let me pull up the whiteboard here and clear this out. And so again, the dice is 1, 2, 3, 4, 5, 6. So what is the probability of not rolling a 1? And so there's a variety of ways to calculate this. One way is that what is not a 1? Well, that would be 2, 3, 4, 5, 6. And so that would be 5 over 6, right? Probability of success is 5, and the total is 6. Another way to do this is that you could do 1 minus the probability of actually rolling the 1. And you could see that this ends up being 1 over 6. And that ends up being 5 over 6 as well. And sometimes it is much easier to do this complement, as the book calls it, than to calculate the actual probability of the not function. And so one important aspect of it, and this is a good example out of the book, is that the complement and the actual probabilities have to add up to the number 1 all the time. And that's what makes the calculation nice and doable. Like here's an example of a weather, right? If there's a 60% chance of rain, what it means is there's a 40% that it's not going to rain. And when you add those together, you get 100%. If we convert that to a decimal, that's the number 1. So the book uses this little c as indication of complement. I've seen other books use different, but we need to follow what we're doing in this book. And so here's the rule. is that the probability of calculating its complement is one way to do it. It'd be 1 minus the probability of the original experiment. So let me go through a couple examples. So, and I did one with the dice, right? So according to Wall Street, 40% of the cars sold in recent years were small cars. So what is the probability choosing a car sold and it's not a small car? Well, if it's not a small car, we could do the complement, right? And so this is the idea of 1 minus the probability of a small car. And you could see it ends up being 0.6 or 60%. Here's another one. And this is the probability of a family of 4 children having 2 girls and 2 boys is 3/8 or 0.375. It's just like flipping a coin, actually. And so what is the probability of a family of 4 not having 2 boys and 2 girls? Here's a good example of this calculation is easier, is that when you do this calculation, it would be the probability of not having the 2 boys and the 2 girls. And so that would be 1 minus that probability, which is 0.375. And you can see that I haven't written and boys here as well, because it implies that if you have 4 children, if 2 of them are girls, then the other 2 are boys. So that ends the recorded lectures for section 3.2. I'm sorry, 5.2.